triangle here is a representation of our hypersurface T. We can consider two surfaces S on it, and then we can consider outgoing light rays that are orthogonal to S, which I call L. Then we can define something called the outgoing expansion of this two surface S, which, so this is just the formal definition, so Q bar is the induced metric on S by the spacetime. It's contracted with the covariant derivative of L, but this is what's more important here. This is, so the physical interpretation of the expansion, which I call theta L, is that if you consider a set of outgoing light rays on S, then that set of light rays, it has some cross-sectional area, which I call delta A. And along the direction of those light rays, there is a parameter lambda. And what the expansion theta L measures is the fractional rate of change of that cross-sectional area along the light rays. So for instance, if the expansion theta L on a two surface was negative, then what physically that means is that light rays on that surface are converging towards each other. That would mean like you were inside a black hole, intuitively. If theta L was greater than 0, that would mean that light rays on S are diverging from each other, which would be like you were outside of a black hole. So an intuitive way to define a quasi-local black hole horizon is a two-surface S on which this expansion theta L vanishes. And so that is the definition of a MOTS, or marginally out-of-trapped surface. So with this definition, we can ask, well, is it a good representation of an event horizon, right? So the answer is most of the time, but not always. And in more extreme situations, things can get quite interesting. And to illustrate this behavior, so my collaborators and I, we did a numerical simulation. What we did is we had a black hole at the origin of our computational domain, and we hit the black hole with a very strong pulse of gravitational radiation. So we shot a shell of gravitational radiation onto that black hole, where the gravitational radiation is located at a distance, a radius of about 15 away from the origin. And for that gravitational radiation, we could adjust the amplitude. We can adjust the amplitude of it. The higher the amplitude A is, the more radiation, the more energy that radiation has. And here is a figure showing the properties of our initial data. So this is amplitude on the horizontal axis, and this is energy on the vertical axis. And this red curve here represents, this is the ADM energy, or the total energy of our spacetime in the initial data. This blue curve down here is the mass of the black hole in the initial data for a particular value of the amplitude A. And the difference between this red curve and this blue curve represents the energy contained in the gravitational radiation. And the interesting thing here is that for the highest amplitude we considered, A equals 0.5, the energy in the gravitational radiation, which is represented by the difference between this and this, is actually larger than the energy of the black hole itself. So if we consider this case of A equals 0.5, then when the gravitational wave hit the black hole will be extremely distorted. And this is something that numerical relativity simulations can handle. So then let's see what happens then to the marginally out-of-trapped surfaces in our simulation under such high distortions. So shown on this slide is during the evolution, all the marginally out-of-trapped surfaces that we locate. Plotted here is the mass of every marginally out-of-trapped surface that we find at each time, where the mass irreducible mass here is just defined as the square root of the area of the surface. And shown here is a time interval where the gravitational radiation, in the vicinity of the time that the gravitational radiation hits the black hole. And at earlier times, so each of these circles represents a time that we find a marginally outer trapped surface. At early times, there's only one circle at each time, so there's only one MOTS at each time. However, around this time, around a little after time 14, new MOTS suddenly appear in our space-time. So in addition to this black circle here, we get two new MOTS that appear with larger masses and as larger areas. Until at a very small time interval, which is this pink shaded region, the same thing happens, and we have 5 quasi-local horizons existing at the same time. So we have 5 black hole horizons representing a single distorted black hole. And then at late times again, we only have 1 quasi-local horizon at each time. So then at late times, after the distortion has left, then things look normal. So this is an interesting behavior of quasi-local horizons. And how does that compare then to the event horizon? So this is shown in this figure here, where this blue curve is the same curve that I showed on the previous slide. But then we show the mass as well for the event horizon in the space-time, which we can find after we finished the evolution. We can go back and then find the event horizon. You can see that for the quasi-local horizons, you have all this more interesting behavior, but for the event horizon, it just increases smoothly and then flattens out. And of course, there's only one event horizon at all times. So that's an illustration of how they can be quite different. And this is just a space-time diagram of that situation, where this silver or gray surface represents how all the marginally outer trapped surfaces, they form a world tube that goes forwards and then backwards and then forwards in time. And here's some red dotted curves, and these are the null generators of the event horizon, the light rays that define the event horizon.
So this is a spherical symmetric calculation.
But this is not a spacely symmetric calculation.
That's not?
Right.
This is not?
So the black hole, the black hole could be spinning or not spinning. That's actually not an important aspect.
But I think the wave,
the wave is
gravitational wave
not,
that impinge on.
So the wave is not spherically symmetric.
Oh, is that right? Oh, okay.
Right.
Right.
It's the wave that we choose. I think was no, it wasn't even axisymmetric. It wasn't even axisymmetric. So this is a full 3D simulation.
Oh, I see. Okay.
Although more details can be found in this paper, where I do an analytical study of the same situation in the Baija space-time, which is spherically symmetric. And a similar thing occurs there, which is quite interesting.
I think I was asking the wrong question, because a gravitational wave cannot be
Spherically symmetric.
Yeah.
Right. That's right. So with that illustration, I hope I've conveyed that the numerical relativity can be a useful tool to use in conjunction with mathematical relativity concepts. And there's still further questions we can ask, still related to quasi-local horizons. Once we've defined a particular quasi-local horizon, we still use that surface to define physical properties of our black holes, like the mass and the spin. Well, what are good definitions then to use? Numerical relativity allows us to investigate the interiors of black holes, not just the exterior. And what are the detailed dynamics in an evolution? If matter falls in, what is the late time behavior inside the black hole? Black hole singularities, we can also look at these and look at how strongly curvature quantities diverge as singularity is approached. is that singularity strong or is it weak? We can look at something called the Hoop conjecture that was proposed by Kit Thorne back in '72. And this essentially says that if you have a distribution of energy and you compress it enough so that you can pass a hoop around it, with the radius of that hoop being equal to the Schwarzschild radius of that energy distribution, then that configuration should have collapsed to a black hole. However, it's a pretty imprecise statement, so can we use numerical relativity to try to make that statement more precise, or can we even find exceptions to say that the Hoop conjecture is not true? And cosmic censorship, proposed by Penrose in '69, says that you should not be able to form naked singularities under generic initial conditions. Well, is that true as well? We can use numerical relativity to try and investigate that. And finally, there's the issue of critical collapse, or critical phenomenon gravitational collapse, first discovered by Chapter in 1993. And in critical collapse, basically a phase transition occurs in your space-time, analogous to phase transitions in statistical mechanics, which is quite an interesting thing. But Chapter did his work for spherically symmetric massless scalar fields, and there has been very little work to go beyond spherical symmetry. And in particular, for critical collapse of rotating gravitational waves, this has been a long-standing challenge in the field. More than 20 years, people have tried and failed. And so this is actually a project that I'm currently working on right now. So here's just a summary and conclusion. Numerical relativity is a useful tool to study strong gravity in general, where analytical techniques break down. And construction of gravitational wave detectors has driven the field to simulate binary black holes, among other compact binaries. And in recent years, our ability to simulate these objects has matured to produce accurate waveforms that we can actually do science with. However, more challenges remain, especially exploring the more extreme regions of parameter space. And besides doing astrophysical problems, we can also study problems that are of more mathematical nature. And I just want to emphasize that from my own perspective, I view numerical relativity as not just a tool for solving Einstein's equations or general relativity, but it can be used to solve any theory of gravity and any problem where strong gravity exhibits interesting phenomena. And so with that in mind, a rich variety of applications still remain for numerical relativity. So that is my talk, and thank you for listening.
Thank you. So can I have a first question? Can you make some comments about the effect of possible electromagnetic field around the black holes? What do people think about, the interaction from electromagnetic field is many orders beyond the gravitational interaction. So it's pretty common to have these baryons surrounding the black holes, creating kind of plasma environment.
Right.
So what do people think?
So I think that so these black holes, astrophysical black holes, probably not just in vacuum, right? Surrounded by gas.
Yeah.
There have been some limited simulations of binary black holes in gaseous environments, and I think that current results show promising signs that with the merger of black holes surrounded by gas and so on, there will be electromagnetic counterparts, measurable electromagnetic counterparts, in addition to just detecting gravitational waves that can be used.
So you don't think that the electromagnetic dynamics will not affect the interaction? Yeah, the dynamics of black hole interactions.
So the interaction of gravitational waves with any other type of matter or fields is very weak, and so that shouldn't have much influence.
Okay.
Now you have this template, hundreds of templates of gravitational waveform.
Right.
Do they look different? Or the experiment, suppose they detect something, and do they have to match all these thousands or hundreds of
Different
waveforms
frequencies,
Right.
to find out the spin parameters or mass? Or
So the pictures I've showed you for the gravitational waveforms all look very similar, right?
right.
So that is mostly because I've chosen a specific orientation of the waveforms so that they look similar. If you have, say, precession of the orbital plane in a binary, then different orientations that you look at the binary from will have different strengths of the gravitational wave. And there will be much more variations in the pattern.
So it's sensitive to the orientation, not sensitive to other parameters in terms of experiments.
Also length, right? Also the length of the waveform, the orientation of the binary, which causes modulations in the waveforms.
So it's more about the orientation. It's not.
More
It's less so for.
I would say the biggest difference between waveforms would be due to the orbital plane's orientation. Yes, I would say that.
Suppose most of your simulations aiming at the LEGO for this gravitational detection. Suppose the LEGO would not find anything. What's the strongest sort of conclusion you can draw from your simulation? Of course, the finding everyone is happy. You probably but if they don't.
Right. I mean, I think that would be an interesting result. I mean, that would, if LIGO is actually operating at design sensitivity, and there are reliable models that say, say, at this sensitivity, if binary black holes really exist, you should detect it, and LIGO doesn't detect it, then that would be saying, right, that there maybe are not these sources around for gravitational waves.
So do you want to say anything about LISA?
About LISA, well, LISA right now is
Too long in the future.
Has it been approved by NISA?
it has not yet, so
Is it likely to be approved?
not in the near future.
Well,
so,
the Chinese part is getting in right now.
oh, the Chinese is doing it.
Yeah, they're putting the money in because there was a severe budget cut last year or 2 years ago. But it's still being planned. So between the time scale, the spatial scale would be definitely different from LIGO.
Right. I mean, LIGO, just in a few years, it should give us some interesting results, even if it doesn't give us, even if it gives us a non-detection, right? And just the construction or the environment of these detectors. So LIGO is constructed on the ground. LISA is going to be in space, where it's free from a lot of sources of noise on Earth, like seismic noise, seismic activity, and also LISA is really aiming for extreme mass ratio in spirals, which is again a different target than LIGO.
So then what your conclusion is, well, maybe there's no such a source nearby, so we cannot do it. So you cannot tell anything about the nature of gravitational wave. Should there be a gravitational wave, or is it just people's interpretation of general relativity?
So, I mean, there are. Well, I guess I should say first that LIGO is not only trying to detect binary black holes, but also gravitational waves from other compact objects, right? Like black hole neutron stars, neutron star binaries, for instance. And it's certainly known that binary neutron stars exist, right? So, if those give off gravitational waves in the right frequency, those should be detected by LIGO. And if LIGO makes a detection and it doesn't look like what general relativity predicts, that's also an interesting thing, because then that might indicate that, well, general relativity is not quite right. There are modifications of general relativity that need to be taken into account. Right? So it can also serve as a test of general relativity.
It's been about half a century since people one of the earliest projects Stephen Hawking would like to do in his 20s. Yes.
Is it possible to simulate other astronomical object like wormhole or something and real life time travel things?
Time travel, wormholes and time travel. Wormholes, it might be possible to do. Simulation-wise, right? I mean, they would require different boundary conditions, different inner boundary conditions. Right now, I talked about black hole excision, how we cut the interior of a black hole away, but for wormholes, you would want to do something different. But that's certainly possible. Constructing initial data should be simple. And evolving, I don't know if wormholes are stable or not, but that might cause problems, and but it should be something that could be looked into.
So, I guess, how? So, you mentioned like, can you extend the amount to the higher dimension, and how much more computing power you might need to,
Right.
if you are faculty here?
So you can extend to higher spatial dimensions. The highest that has been done is 4 spatial dimensions, so 4 plus 1. Extending to higher dimensions, it drastically increases the computational resources needed if you're actually assuming no symmetries. But if you restrict to discretely symmetric or axisymmetric cases, then you can effectively reduce the dimensionality, which makes things more simple. And that's actually the only cases that have been considered so far. I think doing, let's say, a binary black hole in 4 plus 1 dimensions is just way too costly at this point to actually do. But if you consider, say, the axisymmetric collision of 2 black holes, I think that then is something that.
More questions? If not, then let's thank Tony again.